yesterday, we finished with writing the representation formula for spin operator. Do something like this. So, that's as far as we got yesterday. So I basically started by rewriting the spin operator in terms of the spin disturbance by the Jean-Wigner transformation, and then I quote-unquote bosonized for you this string operator, and finally multiplied with the Cj, which sits at the end of the string, and this is what came out. Okay? And so the first thing we want to do now is we want to use this once again to work out what two-point correlation functions are. Okay, and so S minus J plus L S plus J ground state correlator now also would have several parts. There would be a part coming here from the staggered component, and then there would be the parts coming from these other vertex operators. And many of the possible combinations, because there are 1, 2, 3 terms, so in principle, in the two-point function there would be 9 possible combinations, but many of them are just 0, because of this electroneutrality, which was this concept that if you have a correlation function like so, then this always was proportional to delta alpha minus beta. Yeah, you have this both in the right and the left sector, and therefore most of the contributions here actually vanish. And the ones which don't vanish, essentially this with its Hermitian conjugate, so this gives us a C absolute value squared minus 1 to the L. And then you basically have e to the minus 2 pi I r tilde theta tilde of x, e to the plus 2 pi I r tilde theta tilde of 0. And then you can get two contributions from here, which are this with its complex conjugate and this with its complex conjugate, essentially. And modulo the x-dependent part. So it's A absolute value squared minus 1 to the L. Alright. E to the 2I kf x. And here you have now this one here. E to the minus I phi tilde r tilde minus 2 pi I r tilde theta tilde with e to the plus I phi tilde r tilde plus 2 pi I r tilde theta tilde at 0. And this was an x. Yeah. and then the other term where we have e to the minus 2 pi kfx dot dot dot. Yeah, so only 3 terms are non-zero by this principle here. Okay? And these 3 terms now you can work out using our general formula of how to multiply normal ordered products of vertex operators and getting a normal ordered vertex operator back. And what comes out, if you do that, is the following. So you get C absolute squared minus 1 to the L, A naught squared, x squared minus v tilde squared f. X squared well, actually, just to save time, let me look at the time-dependent correlation function straight away. So then I get a time dependence here, no time dependence here, time dependence here, time dependence here. Okay, and then here I get x squared minus v tilde squared ft squared. This whole thing to pi r tilde squared, and then a absolute value squared minus 1 to L a naught squared divided by x squared minus v tilde squared ft squared pi r tilde squared plus 1 over 4 pi r tilde squared. And here we get e to the 2i kfx x plus dft divided by x minus dft plus e to the minus 2i x minus dft divided by x plus dft. Okay? And so that is the final answer. And once again, the structure simply has to do with the fact how these pieces, this piece and these pieces here, transform under Lorentz transformation. So this is a scalar, so therefore it only depends on x squared minus v squared t squared. Whereas here, these once again are components of a vector, and therefore they give you this structure of the result. So that's completely analogous to what we had for the ZZ correlator. But you see that, well, the main differences essentially are these exponents. Yeah, they differ now between xx and zz. Okay? And so typically, this minus plus or xx, which would be the same, decays more slowly than the zz. Yeah? So the transverse correlations in a sense are stronger. Okay. So in the literature, you quite often find a parameterization in terms of what's called a Luttinger liquid parameter. Which is called K. And that is related to this compactification radius, or tilde, by k is equal to 1 over 4 pi r tilde squared. Okay, so that formula essentially allows you to translate these notations I've been using to other notations which are frequently used. And just to give you some limits, so delta is equal to 0, so this xx model, there our radius was 1 over root of 4 pi, that corresponds to k equals 1, and delta equals 1, which is the isotropic Heisenberg chain, xxx model. There, our tilde is 1 over root 2 pi, and this goes to k equals a half. And these are two very important limits. All so that's basically as far as I will go now with this visualization approach. So I really started at 0 and shown you how to arrive after some work, but so not that much work, at a way of calculating dynamical spin-spin correlation functions in this Heisenberg XXX model. So that's quite an achievement in many ways. I mean, to get these out is pretty non-trivial. So what remains to be done now is what I referred to already yesterday. If delta is not small, we don't really know what this R tilde is. Okay, we don't really know what this VF tilde is. So for XXZ we can fix it. So let's just write down how this actually works in practice. And maybe Marton has already told you about this. But so essentially you can use the Beta-Ansatz. to fix R tilde, D tilde F, and KF. And the way this is done is you work out energies and momenta of low-lying excitations in the XXZ chain. So there's a standard procedure that allows you to do this. So basically these Beta-Ansatz equations, they are like quantization conditions for your momenta. So once you know how the ground state and low-lying excitations look in terms of the solutions of these equations, you can calculate energies and momenta as sums over these solutions. And the key essentially is if your system size becomes very large, so if L goes to infinity, if L becomes very large, then these roots, the distance between neighboring Beta-Ansatz roots scales like 1 over L. So therefore the distribution of these Beta-Ansatz roots become dense, and if you have a sum over them, you can turn it into an integral. Using Euler-Maclaurin sum formula, just like I did it for free fermions. And this procedure can be done for any integral model and has been done for most of them. And what comes out for XXZ is a spectrum that looks like so. So we have a thermodynamic piece, extensive piece, which scales the system size. And this is the ground state energy per site of the XXZ chain, which is given in terms of some integral equation in general. I think it more to explain this. Okay, so then there's a correction, E times I times V over 6L. Okay, so that would be a universal correction for the ground state energy. And for a conformal field theory, the general expression is like so. So it would be pi divided, for periodic boundary conditions, it would be pi divided by 6L with a minus sign times the velocity times the central charge. And the central charge of this free boson theory is C equals 1, which is why we get this result. So this is universal, apart from the velocity, which is non-universal. But once again, Beta-Ansatz also tells you what this is. And then there are extra pieces that look like so. 2 pi V over L. And then here you get something like this. Pi R squared L squared plus N squared divided by 4 pi R squared plus sum N equals 1 to infinity L ML plus M minus L, and then plus little o from L to the minus 1. And the momenta, they look like so. It's 2kF n plus 2 pi over L Ln plus m equals 1 to infinity. I should call it L, I should call it m here, sorry. N, that's correct, and N minus N. Okay, so that is what comes out of this big ansatz calculation. So the quantum numbers that specify the excited state that you consider is this little l here, the little n, both of which are integers, and these numbers, capital M. And the nature of these excitations for the XXE chain, for the fully interacting chain, is exactly the same as we saw for the XX model. So this corresponds to adding L spin downs to the ground state. This corresponds essentially to one of these backscattering excitations. You make a hole around Kf and make a particle around minus Kf. And these would be particle hole excitations around the two Fermi points. Now the difference is when we did this XX model, we literally were making fermionic excitations of that kind. Okay? Now for the BD ansatz, what is actually, there's this principle of adiabatic continuity works in the sense that the same quantum numbers still describe the low-lying excitations, but they're now no longer free fermions. Yeah? So now they're really distressed BD ansatz excitations which you make in this way. Okay, now to cut a long story short, this is the result of a calculation, which basically has been done for any integral model of interest. And you can just read off, for example, what is the velocity that you need here? So what is this quantity? Okay, so you can read off what is my compactification radius as a function of delta and magnetic field. Okay, and you can read off what is Kf. Okay, and then you're happy, kind of. So when I say read off, so once again, if you don't have a magnetic field, there are closed form expressions for all of these quantities. But if you have a magnetic field, then all of these quantities are actually given in terms of a solution of some linear integral equation. Where's Martin? Did you write them, or has Martin shown you? Okay, so now combining these two approaches then gives you essentially exact results for the large distance asymptotics of equal time correlation functions. Yeah?
Can you read off also the limit of the critical phase from there?
Oh yeah, absolutely. I mean, so this holds only in the critical phase. So in this in the lateral liquid phase, you get these expressions. Yeah.
But how do you know when it stops?
This is very easy. Well, okay. So if you know BD ansatz, it's very easy. So let me just. So Martin supposedly derived for you this integral equation for the dressed energy, which is the object that's in this TBA equation. So roughly speaking, you have an integral equation which is like so. Now it's a convention. Let me call it plus d mu k of lambda minus mu epsilon of mu is epsilon naught of lambda. Yeah, so that's the integral equation for the dressed energy. Yeah, so this would be the bare energy. Yeah, which is basically the energy of a magnon in excitation at zero density. Yeah, which depends on the magnetic field, depends on delta, and it depends on whether the value of delta is between -1 and 1, or larger than 1, or smaller than -1. But this is so now the integration boundary here is fixed by the requirement that E of epsilon of plus minus A has to vanish. Okay? And whenever you can fulfill this condition for a finite value of A, you basically will have gapless excitations around that point in your rapidity space. And if you work out what the energies are in a large finite volume, you get this. Okay? But at some point, what will actually happen is A will collapse to 0. Okay? And this shouldn't surprise you at this stage, because I told you, for example, this transition, in the phase diagram there were two transitions. This one here was this commensurate incommensurate, that corresponded to emptying out of Fermi C. Yeah? And the same actually happens in the Bethe-Ansatz language, because if A is finite, essentially what you have to do is you have to fill these negative energy state of dressed excitations of spin-ons. Yeah? And then, if A goes to 0, you hit this phase boundary, okay? And now you should complain, which you don't. I mean, so, because I told you this commensurate-incommensurate transition is always free fermionic in nature. But now I'm saying you're emptying out a sea of these spin-ons, which are not fermions, yeah? Which have a non-trivial statistics and non-trivial interactions. So maybe I don't know what I'm talking about, but maybe I do, because actually what happens when A goes to 0, the density in your system becomes very, very low. Yeah? So essentially you go into a limit where the density of your spin-ons goes to 0. And when the density goes to 0, essentially the interactions between the spin-ons, they disappear. Yeah? And what remains is essentially the fermionic statistics. So in this limit, the spin-ons actually do become free fermions again. Yeah? So you can see this on the level of the Bethe-Ansatz. So this is absolutely okay. So now what happens here? Yeah. So I explained to you this transition. What about this transition? This transition actually A goes to infinity. So when I hit this line here, A goes to infinity. And afterwards, your dressed energy looks like so. Yeah, but there's a gap. So which means making any excitation now costs you a finite amount of energy. So you don't no longer get this spectrum. Yeah? So the phase boundaries are easier to get because all you need is this one equation. Whereas to get the other quantities, you need two. Alright, so let me just give you these formulas. So as I said, in general you have to solve these linear integral equations, but in zero field they're very nice closed form expressions. Yeah, if you want to see these integral equations, for example, I mean, Martin wrote them for you, but you also can look in this paper, so point math 04, 12, 41. Yeah, so they're written there. And if you solve them now in the limit of zero field, so if delta absolute value is less than 1 and h is equal to 0, you have closed form expressions. And they are that kf a naught is just pi over 2, so you're exactly half filled. R tilde squared is just 1 over 2 pi squared arc cos of minus delta. And Vf tilde is j a naught over 2 sine 2 pi r tilde squared divided by 1 minus 2 pi r tilde squared. Okay, so in zero field they're very nice simple expressions. Yeah, but in finite field, not. So there's basically you can get them to any desired accuracy by solving this linear integral equation. A linear integral equation, Martin probably told you, is very easy to solve because it's essentially a matrix multiplication. To solve it, you just have to diagonalize a matrix, yeah? And so you basically, if you want your velocity in a finite field to 10 digits or so, you can do it. Yeah. All right. So that's all I'm going to tell you about bosonization, really. So if you have any questions, about what we have done in the last 8+ lectures about the bosonization part, you can ask now, while I erase some of this stuff. Everybody's lost, probably.
You say that you can apply this technique also if you have an interval here.
Oh yeah, absolutely.
But in that case, it is valid only for small values of the interaction.
No.
And so how...
No, and you should have asked me 30 seconds earlier. That was very nasty. You waited until I had to erase the relevant formulas. Yeah? Because now, so what happens if I study a model which is non-integral? So for example, if you just take a XXZ chain, so J1 Sj dot Sj plus 1 plus J2 Sj dot Sj plus 2. So let me look at the model like this. This model is no longer integral. Yeah? So I have nearest neighbor exchange, but also next nearest neighbor exchange. And let's say I start with J2 being small. So, can I bosonize it? Yeah. And the answer is, well, okay, so you can bosonize it. Okay. So you would do essentially the same thing that we did previously. So let's say start with this one here. That you know we can bosonize. I've given you all the expressions now. Okay. And I've even told you what the compactification radius is, the velocity. So here you know everything. Okay. So now you can bosonize this term by doing the same thing that we did when we handled this delta term. Okay, so now I gave you the bosonization expressions for the spin operators. Yeah, just do your OPEs and see what you get. Okay, so now what you see is once again this reduces essentially to quadratic terms that are already present in the Hamiltonian. Yeah, plus a term which I'm going to tell you how to treat in the next lecture. So, but it means, essentially this analysis shows if J2 is small, you still have a Luttinger liquid. So this comes out of this analysis. Now, what you do in practice is you remember that a Luttinger liquid has this spectrum, which is implicitly still written here.
Yeah.
And then now you no longer can calculate the spectrum exactly, because that model is not integral. Yeah? But now what you do is you talk to your friends who are experts in DMRG, yeah? And then you say, well, can you calculate for me the spectrum of some low-lying states? And I will tell you what they are. So for example, go into the sector where I have one overturned spin. Can you tell me what is the ground state energy in that sector? Or can you tell me what the ground state energy overall is in a large periodic system? Yeah? And then they go and they do the calculation and they find for you a spectrum of this form for energy and momentum. And then you say, okay, now I can read off what is actually compactification radius, you know, what is the velocity, you know, so what is kf, which will be actually pi over 2 in this case.
From the solution of the method SAS, I can see that there is a phase in which is valid the Luttinger liquid.
And how it breaks down, you can also see both from the bosonization approach, we will do this next, and from the numerics. Yeah? Because what your friend actually will tell you, if this J2 is larger than 0.2411 ... He will say, well, you know, Bruno, I mean, the spectrum actually doesn't look like that. Yeah? And then you say, so if the spectrum doesn't look like that, I must have gone through a phase transition. Okay? And that's basically how you can tell. So when this spectrum works, it's Luttinger liquid. If it doesn't work, it's something else. But even from within the bosonization approach, you can basically detect the boundaries where things start going wrong. Yeah? So if you run into a phase boundary, bosonization approach will tell you. Yeah? And that's basically the final topic. Okay? So are there other questions? Okay, I still have some stuff to erase, so you can think. So, let's now come back to our phase diagram. So, phase diagram looks like this. And what I've explained to you is I've explained to you the physics in this dimensional liquid phase, which is our bosonized theory, three boson. I've explained to you this transition, and actually in the very first lecture I basically explained to you how to sort out this ferromagnet. Yeah. Ferromagnet is very simple because the ground state, for example, in terms of your free fermions, is just the empty vacuum. Yeah? And then how to make excitation is very simple. So you have done this, we have done this, but how about this transition here? Yeah? I haven't actually told you about what happens there. Okay? So I've told you what is the nature of this phase. Yeah? It's an ordered phase where you spontaneously break the spin between these two ground states, which are the two classical ground states at delta equals infinity, and you acquire nil order. But how do we actually go from the Lagrangian liquid to this antiferromagnetic phase? I haven't told you about that yet. Yeah? And in order to understand this, we have to combine this bosonization approach with another method, which is called renormalization group. And renormalization group will essentially tell us how to understand what happens here. Okay, and this will also answer your question. By looking at this RG, you basically will see, eventually I must go into a different phase. Yeah? Okay, so the next and final topic is essentially Wilsonian renormalization group. Okay, so with regards to RG, so there are many ways of doing this. Yeah? And you might have had some lectures about this from the point of view of relativistic quantum field theory. And that's one way of doing it. So you derive essentially this Calabrese equation for correlation functions based on diagrammatic expansion. Now in these condensed matter systems, this Wilsonian idea of doing RG is much more natural, because when we do condensed matter systems like the spin chains, the field theories we get really are never renormalizable. Because, as I said, so this cutoff we are dealing with is physical. It's a physical scale, and we don't really end up with this free boson theory. We have this free boson theory plus a whole bunch of perturbations to it. So such situations are much easier to deal with in the scheme that I will introduce now. And let me actually, for simplicity, consider what happens as I go along the h equal to 0 axis through delta equals 1. Okay? And I could do the same here, yeah, but to keep the notations as simple as possible, I just consider this case. All right? So now here, my Hamiltonian of the full theory now looks like this. So I have my free boson. But now I have this other term, which I initially just disregarded, which was this cosine. So that was my full theory. Okay, so this is a free theory, but now I add this very nonlinear interaction. So this model is called the sine-Gordon model. Yeah, and it's also a very nice model because it turns out to be exactly solvable. Yeah, by big ansatz, but we are not going to use this here. Yeah? So what we want to do is we want to analyze what is the effect of this extra piece, yeah, on our free boson theory. Yeah? So is this extra interaction important? Do I need to worry about it? Or can I just treat it perturbatively or something of that sort? Okay, now the easiest way of doing these calculations is in imaginary time. So let me just briefly remind you how that is done. So we first go to the Lagrangian formulation. So the Lagrangian that corresponds to this Hamiltonian is simply 1 over 2b dxy squared. And what I will do now is I will drop all these tildes because I'm sick and tired of writing all these tildes. Yeah, so dxy squared minus b over 2 dx theta squared. Sorry, what am I doing? dt phi squared dx phi squared minus lambda divided by a naught squared cosine beta phi. Okay, so that's the Lagrangian I want to analyze, and so V in my case is really this V tilde f, and beta would be 2 divided by r tilde. Yeah, so I just simplified notations a little bit, and I also dropped the tilde here. But now if you just as usual calculate from here the momentum and then look at PQ dot minus L, you get this Hamiltonian back. Okay, so that's the same theory. Okay, so now what we want to do is we want to go to imaginary time. So tau is IT. Yeah? And so in other words, what I'm doing by this mapping, I go from Minkowski space, where time and space variables actually are different, to Euclidean space, yeah, where my second direction, the y direction, will just be v times tau. Okay? And the action, yeah, which is now the time integral of the Lagrangian in real time, maps to this Euclidean action, which has this form. So d squared x, and here I just get a grad phi squared plus lambda divided by a naught squared cosine beta phi. So that would be my Euclidean action. Okay? And the theory is completely equivalent to my quantum model in the end of the day. So what I need to do as usual, I do my calculations of whatever quantity I want in Euclidean space, and then I get a result which depends now on this Euclidean variables x and y. I should say y is simply v times tau. And after I finish the calculation, I just analytically continue back to real time. Okay? But that of course doesn't mean literally I should set tau is equal to it. So I have a function now of a complex variable which will be y, and I literally have to analytically continue the result, and that will give me the corresponding quantity in the Hamiltonian picture. Alright? So this is standard procedure in field theory. So the main advantage is if you work in Euclidean space, all the integrals you have to do, they're nice and you can do them. And you have actually rotational invariance instead of Lorentz invariance, so things are a little bit easier. Okay, so I'm basically assuming you have vaguely heard something like that before, but if you haven't, I mean, so just look at any quantum field theory manual. So this is discussed usually in chapter 1 or so. Okay. Now, there's a
factor of V missing.
V, no, I mean, so V is
spatial derivative.
You haven't changed x. So
sorry?
You haven't changed, you haven't done any transformation on your x coordinates, so there should still be a factor of V out the front.
No, I think it should all work out actually, because yeah, I mean, okay, so y was V tau, yeah.
The only factor is 1/2 that you have.
Okay, there might be a factor of 1/2. So that's overall normalization. Yeah, okay. So I said 1/2 equals to 1.
Okay.
So, yeah. So there's a factor of 1/2, which actually I do want to do. Okay? But so dimensionally things work. Alright? Now, yeah, my partition function is now a path integral. So Z is integral, path integral y e to the minus Euclidean action of phi. Yeah, so this is a function of the field. Right? Okay, so and for later purposes, I want to rewrite it as minus S naught of phi minus S in of phi. And S naught is essentially the quadratic part. You should have told me that I put the factor of 1/2 in the wrong space. Okay. So S naught is the quadratic part, so just the Gaussian part, and S in would be this cosine piece. Alright, and so this is yeah, the usual functional integral over this scalar field. Alright, now we're not really interested in Z itself, but it's the most useful quantity actually to consider. So if you want to calculate physical observables, you would calculate something like a two-point function. Yeah? And so now this is an Euclidean space, and to get the analogous quantity in Minkowski, you have to analytically continue, but this will just be defined as 1 over Z, and then here you have d phi of x, phi of 0 to the minus Euclidean action of phi, and so on and so forth. Yeah? So this is yeah, the usual path integral formulation. So the easiest quantity to look at is this object Z. Place the rho partition function. If I were to add a source term here, this would be the generating functional of my correlation functions, you know, the two-point function and so on and so forth. So I don't want to add the source because for my purposes I don't need it. Yeah? But you could just carry out the entire calculation I'm doing now with the source added, and we'll give you analogous formulas for the generating function. All right. Now, what do we want to do with this? Now, my field, phi, has a cutoff, which I call lambda. And the theory then defined with this cutoff in momentum space has a mode expansion. I'm just writing the mode expansion now. D squared k over 2 pi squared e to the I k dot x phi k. So I don't worry about zero modes and stuff like that right now. So I'm just imagining in a very, very large volume, so zero modes are not so important for what we want to do here. I do something similar to what we did for free boson calculation. So they are also the high momentum modes in the mode expansion I somehow had to suppress, so I suppressed it with this convergent e to the minus 2 pi epsilon factor, which is like a smooth cutoff. So here instead I want to work, because it's easier, with a sharp cutoff. Yeah? So I only take momentum into account inside a sphere, yeah, of radius r, radius lambda. Okay, now the idea is lower the cutoff from lambda to lambda prime and integrate out the modes in the slice lambda prime less than k, absolute value less than lambda, in our path integral. So in other words, the idea is this free boson theory is some low energy, large distance description of our model that we're interested in. And what we're doing now is we're basically saying, okay, if I integrate over the degrees of freedom at high energies, yeah, or at short distances, how does that affect the low energy degrees of freedom? Okay, so that's the question we are asking. And essentially, if you have a scale invariant theory like this free boson theory that we had in this large liquid phase, the answer is your critical exponents, for example, will not be affected, yeah, by integrating out the high energy degrees of freedom. So the only thing that this integrating out will do, it will change your velocity. So the non-universal quantities, or these amplitudes, A, B, C. Okay, now what we want to do is we want to carry out this integration and then look how the action for the low energy degrees of freedom changes if we integrate out this high energy degrees of freedom. So, in order to do that, I think, well, okay, let me write this. We decompose the field into two pieces. So, momenta which lie below the new cutoff and momenta in the slice between lambda prime and lambda. Okay, and I call this decomposition now. The first part already has a name, so it's phi defined with regards to the new cutoff, phi lambda prime of x, and this space here I call h of x. Yeah? So it's a decomposition into slow and into fast degrees of freedom. Okay? And what we'll do is, so now we'll have our break, and after the break we'll basically just carry out the functional integral over these guys. Okay, so we'll continue like in 10 minutes. Now, this was a scalar, but this one transforms as the component this gives you essentially the structure. Now, the quantification, I think that basically, but you see, you have to be a little bit careful because right. So that's a Fermi field, which is essentially part of a spinner. Yeah? So that was like equally size where before by right. And had the chiral boson. Yeah, so chiral bosons, you shouldn't think of them as scalars. No, it's easy because by right was a function only of x minus vt. Yeah? So they're clearly not scalars in the basically, so this only gives you the z moments. So you can always go back to this. I mean, if you like this notation, you can always say z. So you always have something like I alpha right minus right. Okay. So this goes like 1 over z alpha squared over 4 pi. And f e to the minus 1 over z bar. So from these, everything else fails. So now you see, if I combine these symbols, yeah, so basically looking at the opposite times this, then I get something like 1 over zz bar. But zz bar is actually, if we go to the hospital, x squared minus b squared is equal. So that's the scalar. Yeah? So this is how you get it back. if you have these pieces sitting by themselves, you always get. So in other words, in terms of the Lorentz group, so the spiral vertex operators, they have spin, they have component spin.
Sì, ma quella si chiede per forza.
Whereas component spin is the sort of rotations around the Lorentz group. Yeah. And so you can transform them into trivial rotations. They have spin. For example, R, that has spin, it's spin of R, because it's part of the spinner. Yeah. It's the same, exactly. So these have spin, right? So to make it more precise. I mean, so usually we define these component dimensions H and H bar. Yeah. And delta, the spin dimension of the operator is H plus H bar, and the spin is H minus H bar. So now these guys only have H equal to 0. They have H bar equal to 0. And these guys actually have only H1 equal to 0 and H equal to 0. Now, in the end, so the basic principle is this. That's all we have to do. Yeah? And the rest follows. But what I said was in fact correct. I mean, so the structure of the correlation functions, you can write down